Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So in continuation with our lecture on the oxidation reactions, where we were considering the use of common oxidizing reagents for reactions that involve elimination of hydrogen. So today we will discuss the dehydrogenation reactions of phenols, anilines, hydrazines, hydrazones, and hydroxylamine. So the key concepts which will be considered in this lecture are the dehydrogenation reactions. Secondly, we will consider how the phenols and anilines are oxidized to convert into quinone. Then we will consider how we can carry out the oxidation of primary amines to nitrile. And lastly, we will consider how we can oxidize hydrazine, hydrazones, and hydroxylamines. Right, so we'll study each of these in a sequential manner. So firstly, the dehydrogenation reactions, just for a revision. So we know the dehydrogenation reactions are the reactions that involve removal of two hydrogens from a molecule. Right, so since these reactions involve the removal of hydrogen, therefore they are considered as oxidation reactions. So before that, we have considered three different types of these hydrogenation reactions. The dehydrogenation reaction that involves the aromatization. Then we studied dehydrogenation reactions that yielded formation of carbon-carbon double bond. Then we considered dehydrogenation reaction that involved conversion of alcohols into aldehyde and ketones. Now we will consider three different types of dehydrogenation reactions that will involve the dehydrogenation or the oxidation of phenols and aromatic amines to quinones. The dehydrogenation reactions of amines. Then we will consider the dehydrogenation or oxidation of hydrazines, hydrazones, and hydroxylamines. So firstly, we will consider the oxidation of phenols and anilines to quinones. So anilines are also known as the aromatic amines, right? So we'll consider that how we can convert. So the aromatic amines are also known as anilines. So here we will consider how we can convert these phenols and anilines into quinones. Right, so let's start. So before considering how we can convert the phenols and anilines into quinones, we must know what are quinone. Right, so you can see these structures here, these two structures. So any of the compound, any organic compound that contains either of these two structures, so an organic compound that has this structure or an inorganic compound that has this structure, then such compounds are known as quinones. Right, so how we can convert quinones? So firstly, we consider how we can convert the phenols into quinones. Right, so for converting a phenol into a quinone, it is compulsory that a phenol should be either a unsubstituted or simple phenol, right, or a phenol that has no substituent at para position. Right, so if you have a simple unsubstituted phenol, or you have a phenol with no substituent at para position, or you have para-hydroxyphenol, which are also known as quinones, or if you have ortho-hydroxyphenol, also known as catechol, all of these can be oxidized to quinones when treated with a suitable oxidizing agent. Right, so if you have to convert a phenol into a quinone, it is compulsory that the phenol should be any of these. Either it should be a simple phenol with no substituent at all, or it can be a monohydric phenol, means having just one hydroxyl and no substituent at para position. It's important that substituent should not be at para position. Or you may have any para-hydroxyphenol, or you may have any ortho-hydroxyphenol. So when such phenols are treated with suitable oxidizing agent, they are converted into these systems which are known as quinones. So quinone actually exists in two forms. Either they are para-quinone, so this is a para-quinone, or they exist in the form of ortho-quinones, right? So we will study them in shortly here. So firstly, about orthoquinones. So orthoquinones are in general considered less stable than para-Quinone. So we must know the reason here why they are comparatively less stable. So for this reason, if you can just see here the dipole. So there are two polar bonds which are very close vicinity here, and you can see that the ends of dipoles of like charges, means this carbon, this is partially positive, similarly this carbon is also partially positive. So we say that these are the ends of dipoles with same charges or with like charges which are closer together. So these are two carbons, both of these carbons are partially positive, and this is making this system a highly unstable system, right? So if a molecule is to be stable, it is necessary that the ends of dipole with like charges should be far apart, right? So in case of orthoquinones, since these ends of the dipole with like charges are very close together, so that's why orthoquinones are not much stable. Whereas if you see the para-Quinones, so here this polar bond and this polar bond, so both of these are polar bonds, and you can see this carbon which is partially positive and this carbon which is partially positive. So these ends of the like charges are very far apart, and they are in opposite direction, right? So because these like charges, these same charges are at a greater distance, therefore the para-Quinones are more stable as compared to orthoquinones, right? So when we have to name a quinone, right, it's important to know that which aromatic hydrocarbon they are derived from, right? So if a quinone is derived from benzene, then it's called a benzoquinone. And for example, if a quinone is derived from naphthalene, then it will be called as naphthoquinone, right? And if a quinone is derived from anthracene, that will be known as anthraquinone. So just for example, we are here giving some examples. So consider this one, right? So since that this quinone is derived from a benzene ring, therefore it's called benzoquinone. And further, if we consider that the relationship of these carbonyls or the relationship of these oxygens is with respect to each other is 1,4. So one of these oxygen is attached to carbon number 1, and the second oxygen is attached to carbon number 1, 2, 3, 4, right? So since these two oxygens are having a 1,4 or para relationship, that's why these benzoquinones are known as 1,4 benzoquinone or simply para-benzoquinone, right? Right, so this first one, since oxygen has 1,4 relationship with each other, so that's the para-benzoquinone, or also called as 1,4 benzoquinone. So here we have these two oxygens, and you can see their relationship is 1,2, because if this oxygen is attached to carbon number 1, then this second oxygen is attached to carbon number 2. So this benzoquinone is known as ortho-benzoquinone or 1,2 benzoquinone. Now we have this one, so you can see this is derived from this naphthalene, so that's why it's called naphtoquinone. So if the oxygen and this oxygen, if they are having 1,4 relationship, so these are known as 1,4 naphtoquinone, and if these oxygen would have 1,2 relationship, then they would have been ortho-naphtoquinone, right? So here again we have anthracene, and this naphtoquinone is derived from anthracene, so this quinone will be known as anthraquinone. And as you know, the numbering system, so this carbon is carbon number 9 and this carbon is carbon number 10. So this oxygen is on 9th carbon and it's on 10th carbon, so this is known as 9,10 anthraquinone. So always remember that we can have orthoquinone, we can have para-Quinone, but we can never have a metaquinone, right? So it's your assignment to find out why we don't have the metaquinones. So now we will consider how we can oxidize the phenols, right? So when we have substituted phenol, like we have a para-hydroxyphenol, which is also known as a hydroquinone, or if we have the ortho-hydroxyquinone, also known as catechol, then some also call it that pyro-catechol, right? If you have hydroquinone, means para-dihydroxyphenol, then in that case the oxidation of this quinol will result in formation of para-quinone, right? So this is a hydroxyphenol with hydroxy at para position, right? So when we oxidize this molecule, you can see that we are removing this hydrogen from here and this hydrogen from here. So we have removed two hydrogens, right? So since we have removed two hydrogens, that's why it's known as a dehydrogenation. And since loss of hydrogen is known as oxidation, so here we are referring the process as oxidation, right? So dehydrogenation of phenol, if you are using paraphenol, para-hydroxyphenol, you will need a para-quinone. And if you have a ortho-hydroxyphenol, then in that case what you get this ortho-quinone. So we will now consider that what are the reagents, what are the oxidizing agents that are used to convert these phenols into quinone, right? So different common oxidizing agents are available that can oxidize these phenols and anilines to quinone. So remember, the reagents which are used for oxidation of phenols are also used for the oxidation of anilines, right? So these reagents involve the Flemish salt, right? So then we have dichromate. So whenever you use dichromate, you may use potassium dichromate or sodium dichromate. You have to use sulfuric acid with it. Then you may use silver oxide, or you may use permanganate. And whenever you use permanganate, also you have to use the acid along with that, right? So this permanganate and dichromate, they always work when there is an acid along with them. Then you may use lead tetraacetate, or you may use this HiO4, or you may use NBS. So NBS stands for N for nitrogen, and this is bromosuccinamide, right? So when you are using N-bromosuccinamide in presence of water and in presence of sulfuric acid, so under these conditions you can convert these phenols to quinones as well. So you may use of manganese oxide, and when you use manganese oxide, then you have to use bentonite, right? So bentonite is the spot on which manganese oxide is dispersed, and such reaction work in presence of microwave irradiation, right? So you can use this manganese oxide which is dispersed on bentonite, and you have to use the microwave irradiation. So under these conditions you can convert these aniline or phenol into quinones. Otherwise you may also use dimethyl dioxiranes. So these are the reagents which are commonly used to oxidize phenols and anilines to quinones. So we'll see the mechanism, and we will see some examples in which we can carry out the oxidation reaction. Okay, so firstly we can see the mechanism, and we are now considering the mechanism of oxidation of hydroxyphenols, right? So how can we convert the hydroxyphenols into quinones? We are not using the simple phenol for oxidation. So the mechanism of conversion of a hydroxyphenol into the quinone can be seen as a sequence of proton and electron transfer, right? So you can see there will be loss of hydrogen, there can be loss of electron. So once the first step will be deprotonation, means removal of a hydrogen, and the next step will be the removal of electron. Then we will again remove the hydrogen and then remove the electron. So there will be alternate removal of a hydrogen in the form of proton and the removal of electron. So we will altogether lose 2 hydrogens and we will lose 2 electrons, right? So just see the mechanism firstly. Suppose we have this para-hydroxyphenol, right? The first step will be deprotonation. So after deprotonation we will form a phenoxide ion, right? You may see there's a negative charge here, right? then what will happen that this phenoxide will remove an electron. So here you can see there is a negative charge, but when an electron is removed, this negative charge will be converted into a radical, right? So ultimately we have converted this phenoxide ion into a phenoxide radical, right? So next step will be, so this radical will be delocalized and there will get the removal of this proton once again, right? So when a phenoxy radical is formed, then next step will be removal of proton. So you can see this proton has been removed, right? So we will get a negative charge again here, and this radical anion, why we are saying that radical anion, because we are here having a radical, a free radical here, and we are having a negative charge here, right? So therefore we are calling it as radical anion, right? This radical anion is known as semi-quinone, right? Why is we are saying it's semi-quinone? Because it's just resembling like a quinone, but it's halfway. So what's missing is the double bond here, and there should be no radical or anion. So if we create a double bond here and double bond here, and we remove this free radical and a negative charge, so that will be a quinone, right? So since it's halfway to the quinone, it is resembling very much like a quinone, so that's why it's known as semi-quinone. And the semi-quinone is basically a radical anion, right? So next step will be, so we will again eliminate another electron from here, and as a result we will form the quinone, right? So this is the mechanism. So you must remember that all of these intermediates are resonance stabilized, alright? So this is the mechanism for the dehydrogenation of a hydroxyquinone. Okay, so firstly we'll consider what do we mean by Fremis salt, right? So in the slide, when we considered which reagents can be used for the oxidation of phenols and anilines to quinone, the first on the list was Fremis salt. So this is a very effective reagent for such oxidations. So firstly we will study what is Fremis salt. So Fremis salt is a very stable salt and it is water soluble. And how it's prepared? It's prepared by oxidation of sodium hydroxylamine disulfonate. So this is sodium hydroxylamine disulfonate, right? So what do? We carry out oxidation of this salt, right? And what happens for this oxidation? We make use of potassium permanganate, right? So why it's called oxidation? Because we are causing the removal of this hydrogen, right? So loss of hydrogen is known as oxidation. So in this reaction, when we are using potassium permanganate, we are causing the loss of this hydrogen, right? So ultimately we have removed this hydrogen and we have also replaced the potassium, sodium with potassium ion, right? So this potassium salt with hydrogen removed, this is known as Fremis salt. And Fremis salt can very effectively cause the oxidation of phenol. The reaction works very well if we have a substituent at ortho position, right? So if we have a simple phenol with a methyl at ortho position, what we get? We get the para-Quinone, right? So we get the second oxygen at fourth position to this oxygen atom, right? So we are not giving here the mechanism for how this Fremis salt work, but what it does, it creates a quinone, it creates an oxygen, it sends oxygen at para to this hydroxyl, and it works very well if there is an ortho substituent available already, right? So what we'll get a oxygen at para to this hydroxyl group. So this hydroxyl group will be converted into carbon-carbon double bond, and here we'll also have a carbon-carbon double bond here, right? So here is how it works, right? So we can have some other examples. So here we can see that in case if you just compare the oxidation of phenols and oxidation of alcohols, because in earlier lectures you saw that Phenols and alcohols are quite the same. The only difference is that the alcohols have an alkyl group while phenols have an aromatic group, right? So in general, the phenols are very easily oxidized as compared to alcohols, so we don't have to make use of very harsh conditions, right? So alcohols need more severe conditions while phenols require a much more milder conditions. So why is that so? Because phenols can be easily oxidized because the phenoxide, which is formed as an intermediate, is very much stable, right? So we can easily oxidize the phenols. So you saw that oxidation of phenols can be carried out with different reagents. You can make use of sulfur oxide. You may use of this chromic acid, and you know that chromic acid cannot be stored for longer. So how we create chromic acid? We make use of sodium dichromate or potassium dichromate with sulfuric acid, right? So you may cause the oxidation of phenols by making use of silver oxide or chromic acid or other oxidizing agent which we're including in the list. So suppose we have this catechol, these two hydroxyls, they are ortho to each other. So in presence of silver oxide and in presence of ether, so we can convert this system into an ortho-quinone. So mechanism of formation of ortho-quinone from this ortho-hydroxyphenol, and the mechanism for formation of para-quinone from this para-hydroxyphenol is the same. So there is no change in mechanism, right? So mechanism for formation of ortho-quinone and para-quinone is the same, right? So you can use silver oxide for the oxidation of para-hydroxyphenol, or you may use this chromic acid for the oxidation of ortho-quinone. But in general, as mentioned earlier, that the ortho-quinones are not stable as compared to these para-quinones. Okay, so we have some other reagents which can be used. Suppose we have dihydroxybenzene, that's suppose we have this hydroquinone or we have this catechol. So we can convert this hydroquinone into quinol simply by using of chromic oxide. You can see just in 5 minutes at room temperature, so we can convert this dihydroxybenzene into quinol. So reaction is very fast. Similarly, if you see that this is ortho-hydroxyphenol and you are converting into orthobenzoquinone, so this is potassium ferricyanide we are using, right? So since although mentioned that this orthoquinone is not much stable, so you can see that formation is much rougher. So you have to make use of 24 hours at 30 degrees C. So you don't have to raise temperature, you just have to give more time because this orthoquinone is not much stable, right? So you can make use of this reagent chromic oxide, or you may make use of potassium ferricyanide for oxidation of these reactions. But one thing that's very important for you to know, that quinones can be reduced to hydroquinone very easily, right? So just the way hydroquinone is converted into a quinone can be converted into hydroquinone, right? So this is the catechol. This catechol can be converted into orthoquinone, and this orthoquinone can also be converted into catechol. So both these reactions are reversible, so they can be reversibly reduced again. So if you have to reduce this orthoquinone, just what you do is that you use of this tin chloride in presence of water, right? So under these conditions, that's again reduced to form this hydroquinone. Similarly, this orthoquinone, if you react it with sulfur dioxide in presence of water, it is converted into this system, right? Okay, again we have this anthraquinone, and how can we make anthraquinone is simply that this conversion occurs in the presence of air, right? What you have to do is just place this anthracene in air for some time, and what happens that will be air oxidized to form this anthraquinone. And if you can see that this anthraquinone that has lost aromaticity in the central ring, right? So the central ring is not resonance stabilized. Not resonance stabilized because during this oxidation, and this resonance stability of aromaticity of this ring is lost, while these two benzene rings, they will have their aromaticity retained, right? So in this way we can oxidize the phenols, right? You can make use of air oxidation, just like here you can make use of the dichromates, you can make use of the potassium permanganate, you may use silver oxide, you may use potassium ferricyanide, or you may use a fremisol. So all of these reagents are very effective in converting the phenols into the quinone. So next, let's see that how we can oxidize the anilines to quinone, right? So that's an aniline, that's an aromatic amine, that's a quinone, right? So the aromatic amines or the anilines, they are readily oxidized to give the para-quinones, right? So you cannot get the Ortho-Quinone from aniline. This is one thing that you should know, right? So if you have a simple phenol, you can get the para-quinone from a simple unsubstituted phenol. You can get Ortho-Quinone only when there is a hydroxy at ortho position to the phenol, right? So you can get only the quinones in case if you have a system like that, right? Then you can get the Ortho-Quinone. But if you have a simple unsubstituted phenol, then in that case you cannot get an Ortho-Quinone, you get the para-quinone always. So here we have an aniline, so there is no hydroxyl group, there is no nothing here. So what happens that when we carry out the oxidation, so this aniline will always yield para-quinone. So with oxygen here at para position, right? So which reagents are used for the oxidation of aniline? The reagents that were useful for the conversion of phenol into quinone will be the same as the reagents that are required for the conversion of anilines into the quinone. So next we'll see what's the mechanism behind this conversion, right? So just like in the previous case where the mechanism involved the formation of radicals in aniline, so in case of aniline the mechanism is just the same. So we not much elaborate this mechanism, but firstly consider that we have an aniline. So that's an unsubstituted aniline. So then oxidation, so this symbol means oxidation, right? So we can make use of any of the reagents which were listed in the list earlier. So in presence of oxidizing agent, what happens that this aniline is converted into radical cation. That's something different. So in the previous case we got the radical anion, the semiquinone, but here in the first step we will get the radical cation here. And what happens that there will be a presence of water, right? So we'll add hydroxyl source, right? And there will be elimination of water followed by this addition of hydroxyl radicals, right? So this hydroxyl radical which we have added will enter at the para position here, right? So there will be loss of water, the two water molecules, since we have added two hydroxyl radicals. So one of the hydroxyl radical will get attached here and other will be lost with the water. So what happens that we get this intermediate imine type species, right? So there will be a carbon nitrogen double bond here. So you know from basic reaction chemistry that if you treat this iminic system with water in presence of an acid, so you get the replacement of this nitrogen with oxygen, right? So what happens that when we add water to the system, so this NH has got replaced with water. Again, we are not going in detail about that mechanism, how we can substitute this nitrogen with oxygen. So if you ask me, we will be elaborate about that as well, right? So that's the mechanism that initially starting from the aniline we get oxidized aniline in which we have got a radical cation, and the next step when we add some hydroxyl source as hydroxy radical, so what happens, this hydroxy radical will approach that's para-carbon, and next by elimination of hydrogen, by elimination of electrons, elimination of water, we get this semiquinone type species. right? And then this imine group that will be converted into carbonyl group by addition of water. So that's the mechanism when we have unsubstituted aniline, right? And that will also be the same mechanism when we have an unsubstituted phenol. So in case of unsubstituted phenol, the first step will be the creation of that radical cation, and the next step will add some hydroxy radical source, and then there will be elimination of water, and then we'll get this quinone, right? So in case of if you're using unsubstituted phenols, then you don't need to add water to convert that into this quinone, because this, instead of formation of this iminic type species, you will get the quinone itself, right? But in case if you have an aminophenol, that's an aminophenol, right? So we have an NH2 group and an OH group. What happens that in that case the mechanism will involve the sequential loss of hydrogen and electrons, right? So firstly we will get this loss of hydrogen in the form of proton, so we'll get a negative charge just like in case of phenols. Then we will result in a loss of electron, so we'll get a negative charge, a radical here, sorry. So firstly an anion, then a radical, then loss of proton, get a semi-quinone type species, right? And then we get an imine type species like that here. So in order to convert this imine type species into quinone, what we do, we'll add water, right? So the addition of water to this iminic type species will result in conversion of this nitrogen, replacement of this nitrogen with this oxygen, right? So in this way we can convert the aminophenols to para-Quinone, right? So this is the method. So whenever you have a phenol, you can convert that into quinone. Similarly, when you have an aniline, you can also convert them into the quinone. So next we'll consider that how we can cause the dehydrogenation of primary amines, right? So that's the primary amine. So what's the different about the primary amines, secondary amines, and tertiary amines from the rest of functional group is that, so when we say primary amine is an amine in which nitrogen is attached with just one group. So if nitrogen is attached with two carbons, then this nitrogen will be considered as secondary. So it doesn't matter if this R group is primary, secondary, or tertiary, right? So if just one group is attached to this nitrogen, nitrogen is considered as primary amine, and if two groups are attached to this nitrogen, that will be secondary, and if three groups are attached, that will be tertiary. So it doesn't matter if the groups attached to this nitrogen, these groups are themselves primary, secondary, or tertiary. It's just the number of groups attached to this nitrogen that matters. So when we have to carry out the dehydrogenation of amines, it's necessary that this amine should be primary, right? So when primary amines undergo dehydrogenation, they form nitriles, right? So this R bonded with this carbon triple bond nitrogen, so this is known as the nitrile functional group. So in inorganic chemistry, we say this carbon nitrogen triple bond as cyanide or cyano group, but in case of the organic chemistry, so this functional group is known as nitrile. So primary amines, when they are dehydrogenated, when they undergo the removal of hydrogens, so one hydrogen from nitrogen and one hydrogen from carbon, so there is intermediate formation of a carbon nitrogen double bond, which is known as imine, right? So firstly we will get an imine here, and that imine will further undergo dehydrogenation. So ultimately the dehydrogenation of this amine, primary amine, will result in formation of nitriles, right? So whenever we carry out the dehydrogenation of amines, it's the nitrile we get. We never end up with an imine, right? हमें imine नहीं मिलता, हमें जब भी मिलेगा हमें हमेशा nitrile ही मिलेगा as end product. So there are different conditions which are used for the dehydrogenation of amines. So we can use different reagents. For example, we may use of lead acetate, right? So you may say lead tetraacetate. We may use of sodium oxychloride. The sodium oxychloride is also known as sodium hypochlorite, and it's bleach. आपके घरों में जो common bleach इस्तेमाल होती है, that's sodium oxychloride, right? So we may use of bleach, we may use of lead tetraacetate, or we may use of K2S2O8 in presence of nickel sulfate, or we may use of trimethylamine in presence of air and in presence of osmium tetroxide, or we may use of ruthenium metal. So this is ruthenium metal, and in case if you're using ruthenium metal, you have to make use of alumina and in presence of air. So this reaction takes place in presence of air. Similarly, this reaction in which you use cuprous chloride, and when you use cuprous chloride, again we use this air, and this reaction is carried out in open air, and you have to make use of this pyridine. So with these reagents, you can convert these primary amines into nitriles, right? So next we'll consider that how we can oxidize the hydrazines, hydrazones, and hydroxylamines. So one by one we'll see, and we'll consider that how we can carry out such transformations. So firstly, the hydrazines. So this molecule is known as hydrazine, right? So when you have a nitrogen single bond like that one, alright, so this molecule is known as hydrazine, right? So in this specific case, we have attached two benzenes, one to each of the nitrogen, right? So one benzene is attached to this nitrogen and one benzene is known as attached to this nitrogen. So this molecule will be called as 1,2-diphenylhydrazine, right? Because one phenyl is attached on this nitrogen and one benzene is attached to this nitrogen, so the name will be 1,2-diphenylhydrazine, right? So whenever we oxidize these hydrazines, so it will cause the removal of hydrogen from this nitrogen and hydrogen from this removal. So we are causing the dehydrogenation reaction, so we'll get a double bond here, right? That's product. So this is known as 1,2-diphenyldiazine, right? So ene indicates the presence of a double bond, and azine, so aza is an old name for nitrogen, right? So there is aza means two nitrogens, and there is an ene between them, so that's the name reflects. So we have two phenyl groups, one is attached on nitrogen 1, other is attached on nitrogen 2, and there are two nitrogens, which is indicated by the name aza, and ene means a double bond. So whenever we oxidize a hydrazine, we always get the diazines, right? So whenever you have to convert a hydrazine into an ene system, meaning with a double bond here between them, so this is known as the aza compound, right? So this diazine, basically that's an azo compound, right? So whenever you have to convert this hydrazine into an azo compound, it's compulsory that this hydrazine should be disubstituted, right? So if there is one substituent missing from here, then in that case you don't get this azine system. It is compulsory that this hydrazine must be disubstituted with one substitute on nitrogen and other on the other nitrogen. So if one of the nitrogen does not have a substituent, in that case this reaction does not occur, right? So remember that when you have to convert this hydrazine, or you have to oxidize this hydrazine into this azo compound, always ensure that you have two substituents on these nitrogen atoms, otherwise this oxidation will not occur. Let's consider that we have a system in which there is one substituent, right? What will happen when you carry out the oxidation? Then what happens that you get an azine, this diazine, so di means to nitrogen, and azine, ene means there is a double bond. So what happens that this medium will undergo an elimination reaction, right? So this azine will not stay like that, so it will undergo elimination. So we'll get elimination of nitrogen from here. So this nitrogen has been removed to nitrogen gas, and this hydrogen gas attached here. So instead of getting some other compound, when you use a system like that, so there will be elimination of hydrogen and followed by the elimination of nitrogen gas. You will get benzene as the end product, right? So never ever try the dehydrogenation reaction of hydrazines when the both of these nitrogens are not substituted, because if they are not substituted, or if one of them is not substituted, then there will be loss of nitrogen gas from the medium, right? So which reagents can be used for such oxidations? So we can use different reagents. So you can make use of sodium oxybromide, so that's also bleach, oxidizing agent. You may use of mercuric oxide, HgO. You may use of potassium ferricyanide. So whenever you use potassium ferricyanide for such reactions, so such reactions will take place in presence of phase transfer conditions. You have to use some phase transfer reagents for such reactions. Right? Then we have the oxidation of hydrozones. So if you are trying for the oxidation of hydrozones, so what will happen if you carry out the removal of hydrogen, right? So in case of hydrozones, this is a hydrazone, right? So you have carbon nitrogen double bond, and this nitrogen is singly bonded to another nitrogen. So this structure is known as hydrazone, right? So whenever you have to oxidize the hydrozones, what happens that two of these hydrogens are lost, and you get a diazo compound. That's a diazo compound because it has two nitrogens, right? So in order to oxidize the hydrozones to form diazo compounds, what you can get, you can make use of mercuric oxide like previously. You may use of silver oxide, you may use of manganese oxide, or you may make use of lead acetate in the form of lead tetraacetate. Right, so these are the reagents which are used for such conversions. So last you will see that if you have to oxidize these hydroxylamines, right, this is hydroxylamine because that's an amine, and this amine is attached with the hydroxyl, right? So this structure is known as hydroxylamine. So whenever you cause the dehydrogenation of hydroxylamine, so one hydrogen will be lost from oxygen and one will be lost from this nitrogen. So we'll get a double bond between nitrogen and oxygen, right? So when you have a nitrogen doubly bonded to an oxygen like that one, so this functional group is known as nitrosyl, right? So in case if nitrogen has another oxygen, that's called a nitro group. But when we have only a double bond between nitrogen and oxygen, only one double bond between nitrogen and oxygen, then this functional group is known as nitrosyl. So whenever you oxidize, whenever you dehydrogenate a such compound, so hydroxylamines, then in that case you always get the nitrosyl compound. So the reagent normally used for this purpose is acid dichromate. So you can use of sodium dichromate in presence of sulfuric acid, or you may use of potassium dichromate in presence of sulfuric acid, right? So in today's lecture we saw that how we can oxidize the phenols and anilines. So both of these compounds, the phenols and anilines, when they oxidize, they form the quinones. And we saw how we can oxidize the hydrazines, and whenever we convert the hydrazines, they yield the azo compounds, right? And it's important that the hydrazine should be disubstituted. Each nitrogen should have a substituent, because when either of the nitrogen has no substituent, then in that case we observe the loss of nitrogen, right? Then we saw that how we can convert the hydrozones, and when we oxidize the hydrozones, we get the diazo compound as well, right? And we also saw the different reagents which are used for such conversions. And lastly, now we have seen the oxidation of hydroxylamines. So when we oxidize the hydroxylamines, we get the nitrosyl benzene. The reagent for that purpose is acid dichromate. I suppose that you have understood the lecture completely. Thank you for your patience.